Before we proceed, we need to have basic knowledge about the cloud computing, reinforcement learning, and deep neural networks. Cloud computing is the delivery of computing services, including server storage, database, networking, software, analytics, and intelligence over the internet, to offer faster innovation, flexible resources, and economies of scale. Reinforcement learning is a simplistic definition, is learning best action based on reward or punishment. There are three basic concepts in reinforcement learning: state, action, and reward. State describes the current situation. For a robot that's learning to walk, the state is the position of the two legs. A deep neural network is an artificial neural network with multiple layers between the input and the output layer. Each mathematical manipulation as such is considered a layer. A complex DNN have many layers, hence the name deep networks. DNN can model complex nonlinear relationships. IoT will greatly facilitate our daily life and make services more intelligent, such as smart homes, transportation, healthcare, manufacture, and factory. Fog computing and caching that move the network resources from the cloud to the edge has been proposed to accommodate future IoT services. Edge equipment will enable edge equipment with local computing and storage capability, and thus localized services including communication, computation, offloading, and content caching. The emerging software-defined network, which splits the function of the network device into control plane and data plane, provide a flexible centralized network management that benefits the edge computing and cached services. This paper simultaneously addresses the issue of the content caching, computing, offloading, and radio resources allocation together and propose a joint optimization solution for the fog-enabled IoT. The content caching and on-off switch of the base station are considered together to minimize energy consumption. Almost all algorithms mentioned in this presentation are based on the assumption that the complete system model and the dynamics of environment can be accurately obtained. However, such as an assumption is usually impractical in IoT environments. So the authors of this paper decompose and solve it with alternating direction methods of multiplier ADMM to find a solution to the convex problem for the fog-enabled Internet of Things problem. The biggest challenge for reinforcement learning is to handle applications with extremely large number of state and action. As deep learning became a hot research topic recently, exploiting the deep neural network, or DNN for short, to estimate the value function in RL, which means reinforcement learning, can provide more accurate regression or approximation. Enhancing traditional RL with DNN create a promising approach, named the Deep Reinforcement Learning, which is good at handling complicated control applications, such as gameplay and robotic control. The authors of this paper provide a joint optimization solution for content caching, computing offloading, and radio resource allocation in the fog-enabled IoT, with the objective of minimizing the average end-to-end delay for all services requests. Let's start with this presentation's highlight. Since computing and storage resources are closer to the user terminal and data source, fog-enabled Internet of Things (IoT) will reduce the need for backhaul bandwidth and decrease delivery latency and can support computing intensive and delay-sensitive services. And as mentioned in the previous slide, the authors of this paper provide a joint optimization solution for content caching, computing offloading, and radio resources allocation in the fog-enabled IoT, with the objective of minimizing the average end-to-end delay for all services requests. And for number 3, the natural policy gradient method is used to avoid converging to the local maximum. Now moving to point 4, this paper simultaneously addresses these issues in fog-enabled IoT and use up-to-date advancements in model-free deep reinforcement learning, for short RL, to learn the policy that can minimize the average end-to-end latency. And the last highlight in this slide, this technique of fixed target network and experience replay are adapted to avoid divergence of the deep RL algorithm. The authors of paper cache enabled heterogeneous cellular networks comparison and trade-off. Analyze the systems that install cache storage in edge routers, base stations, or user devices, UE for short. Many research papers have looked into the issues of content popularity, content search, and content placement. In a study, Fundamental Storage-Latency Trade-off in Cache-Aided NeMo Interface Networks, wireless caching and interface control are examined together, and the trade-off between cache storage and service latency is examined. The joint content caching and request routing scheme is proposed on the complexity of optimal request routing and content caching in heterogeneous cache network paper to minimize the content latency. The authors show that the joint optimization problem is NP-complete in both congestion-sensitive case and congestion-insensitive case, and to find the approximated solution for both cases. In computational complexity theory, a problem is NP-complete when a brute force search algorithm can solve it, and the correctness of each solution can be verified quickly, and the problem can be used to simulate any other problem with similar solvability. Recent advances in the field of machine learning, especially the DNN, deep neural networks, has been widely used for image processing and language understanding. The double Q learning algorithm proposed in the deep reinforcement learning with double Q learning paper, where the action choice is decoupled from the target Q value generation in order to acquire better policy evaluation with many similar valid actions. The algorithm can be used to learn the policy that can minimize the average end-to-end latency. This paper simultaneously addresses these issues in the fog-enabled IoT and use up-to-date in development in model-free deep reinforcement learning to learn. The authors of this paper propose an actor-critic deep reinforcement learning algorithm to learn the optimal stochastic policy for content caching, computing offloading, and radio resources allocation. The edge router decide how to assign fog nodes and their spectrum to each requesting services, and whether to store the requesting content or not, and where to perform the computation tasks, and how many computational resources blocks should be allocated if performed at the edge, with the objective of minimizing the average service latency under constraints. The natural actor critic deep reinforcement learning algorithm with fixed target network and experience replay is broken down into the following steps. First, the actor creates a parameterized stochastic policy, and the critic defines a parameterized value function with random weights, theta t and wt in both target networks. The actor generates actions at, at a time t according to the current policy pi theta as and environment state as t. The reinforcement learning agent observes the next state of the environment as t plus 1 and reward rt, and stores the tuple hst at rt as t plus 1 in the experience replay buffer d. Sample random mini batch of L tuple from replay buffer. For any example I in sample L, the critic estimates the Q value approximation QW SIT AIT and calculates the TD error that indicate criticize whether the action or the current policy perform well or poorly, and update its parameter W using the averaged value from the mini batch to minimize the loss function. For any sample I in sample L, the actor calculates the natural gradient using output or the loss function and estimate Q value, and update its parameter theta towards the averaged gradient over the mini batch to adjust the action probability. And for the last step, it replaces the parameter of both target network using current estimated parameter of their primary network with the rate t once every x iterations, and t denotes the rate to upload the target network towards the primary network. As can be seen, the number of fog points on the objective function towards steepest ascent nodes, and user equipment remain unchanged at each decision time. When looking at the best management area of an edge router, when using the standard gradient approach, the service type flag of each user equipment can be fixed for a specific surge, the optimum towards the steepest ascent direction. The duration and each service request can be made from certain location that lead to a local optimal point around zero point 0.9 and 2.4, which is not the true optimum. The system reward archived by the proposed deep reinforcement learning strategy fluctuate around 2600 when simply considering radio resource optimization without content caching capability. The system also reward are the lowest when we use the actor critic deep reinforcement learning solely for content caching, without considering video efficiency. When we adopt the actor critic deep reinforcement learning only content caching without considering the radio resource optimization, the system reward is always the lowest. In conclusion, in order to reduce the service latency in fog-enabled IoT, this article solves the joint caching, computing, and ready resource allocation challenge. We use model-free reinforcement learning framework to handle the joint decision-making problem because the virus environment is stochastic. The critic value function are approximated using a deep neural network, and the actor parameterized policy is represented by using another deep neural network. With the help of the critic, the actor part develop a policy in the gradient ascent direction. To prevent the deep reinforcement learning algorithm from diverging, the fixed target network and experience reply approach are used. Natural policy gradient method is used to avoid converging to the local maximum. Evaluation results are given to demonstrate the learning capacity and the performance of the proposed algorithm.
Now moving to the second paper in our team, which is working on the Internet of Things. Firstly, we'll introduce what an Internet of Things means and what technology is talking about. With the emergence of the Internet of Things, billions of the physical objects are connected through a network for collecting and sharing information, which can improve various aspects for the daily lives, including smart transportation, smart city, smart home, and smart agriculture or smart water, and also for the waste management. The main objective of the IoT applications are to minimize the latency and processing time while utilizing the computing resources efficiently. Most of the physical devices in IoT are embedded with the sensors and participate in the application which require processing data locally or offload to a suitable computing device. And then we'll talk about how we can introduce or how we can implement this IoT device, this IoT technology. Firstly, we will talk about the CDC. Most of which is the cloud data center. Most of these applications are offloaded to the CDC, which has enough resources for the processing and storage. However, the dramatic growth of the IoT applications and the sensors across the globe lead to the huge amount of real-time data, which is to be transferred to the centralized cloud data center. The Cisco Global Cloud Index estimates that the data produced by the various physical objects and machines would be 500 databytes within 2019. However, the global capacity to transmit the data to the centralized cloud data center is at most 10.5 zettabytes. As a result of this offloading, the application to the CDC can increase in the burden of the network, which causes the network congestion and increases the latency. So for this problem, we have another technique which used the fog computing. To tackle the above mentioned challenge, there is an emerging computing paradigm known as fog computing, which offers the cloud services at the edge of the network with a limited processing and storage capacity. The fog computing has drawn extensive attention of the researchers for the processing delay sensitive tasks locally with the help of the fog computing. The real-time tasks are offloaded to the local fog devices for getting better services with a minimum latency. The most popular and useful fog devices are Raspberry Pi, network switches, routers, and micro data centers. However, due to the limited resources capacity, most of the resource-intensive applications do not fit for the processing in the fog devices and are still offloaded to the CDC. Now we will introduce what's the problem have now. The problem that we need to know that the selection of the fog devices is multi-objective optimization problem, which is called MOP. As we know that, however, with offloading data to the fog devices incur minimum latency and cost as compared with offloading to the CDC, this initiative idea is to offload the delay-sensitive real-time task to the local fog devices that can meet the resource requirement of the tasks and achieve the trade-off between the cost and latency. As we know, the IoT device should not only check the resource availability and workload of the fog devices, but also check the latency and the cost for the processing and transmitting an application. Consequently, the selection of these fog devices is a multi-objective optimization problem. As we know that this MOP is used to find the optimal solution using more than one optimization function, and we will going into details in the next slides. And we know that designing an efficient algorithm or finding an optimal fog device using MOP strategy remains challenging and has not been investigated widely. Hence, the main purpose for this paper that we are talking about is to design an efficient algorithm for finding a suitable fog device using multiple quality of service objective in the dynamic IoT environment. There is a swarm intelligent technique, which is simple as SI and evolutionary computation are shown to be powerful method for the solving a more efficient. This is a technique for the mob. Among many others, accelerated practical swarm optimization, which is called an APSU. Will be used in this paper. It is very attractive SI technique which can solve the mob more efficiently. An APSU is modified version of we'll talk about APSU for the next slide, and we just need to know what an APSU is called, and it will go into details. This APSU is a modified version of the practical swarm optimization technique. The standard PSO, which is the practical swarm optimization, uses the best of the individual and current global best global best individual. So we firstly get the individual for the best and the global best for finding an optimal solution. However, an APSU use the current global best individual only for finding an optimal result, which increase the convergence speed of the particles and reduce the randomness of as iteration proceed decrease. So going to the related work, as we said before, that we'll go into details about the mob. As we know nowadays, most of the real world problems in the distributed environment can be formulated mathematically, which with a certain goals or objective, which are optimized by various heuristic or meta heuristic strategies while meeting the relevant constraints. This function shows a type of the mob functions, which has more than one objective function, and there is the subject with the constraints. There is equality constraints or non-equality constraints. Here, as we know that x1 and x2 and x3 and x4 for the function is m-dimensional decision vector in the decision space, and we have f as an objective function or objective vector which consists of n objective functions, as this f bigger f is contains a number of objective functions maps to the m dimension vector, as we say that we have x in every f, and in general the objective of the mob are conflicting, as we can the single best solution of all of them may not exist at the end. Then we will talk about the technical overview for the apps that will be used in this paper. The PSO technique is designed based on the behavior of the bird or the fish schooling in the nature. The PSO technique searches the space in the space for an objective function for adjusting the position of the particles in the quasi-stochastic manner. Each particle has been requested by its own velocity and position. As a bird, a particle I keep track of its best position in the space by b best, which represent as shown in this figure. We have number of particles, and this is the number of best positions that we have. The global base position, which is one of this position, is called as J star. The velocity defined of the movement of the particle, which has its own magnitude and direction, and defined as follow as shown in this figure. As we know that the velocity is defined as the movement of the particle and has its own magnitude and direction. Now uh, we know that the position of the particle for P is represented as shown in this figure too, and we just need to know what some of these samples in the equations. We have Vi and Xi, which represent the velocity and the position as shown, and position of position vector of ith particle. We have like bird, and we have sigma 1 and sigma 2 in the velocity equation. These symbols are two random uniform variables which values are in the interval of 0 and 1. And the standard PSO techniques use both the current BG best and location and individual best location, which is B best, as shown in the other this is the B best and we have G best. As no, it's for the globally the best. The B best location is useful for PSO to increase the diversity and the quality solution. However, this diversity should increase the randomness of the problem, and there is no compelling to use individual best unless the optimization problem is highly multimodal or nonlinear. The simplified version of PSO technique is used to the G-best location of the particle to accelerate the convergence of the problem. As we know, the APSU is simplified version, so we need to speed up this. So the APSU is only use the G-best location of the particle to accelerate the convergence of the problem. As shown in this figure, we have here the position and we have the velocity. Then we will talk about the implementation. Firstly, we need to know what we will do in this paper. They have designed a new multi-objective offloading, which is MO strategy, for the hierarchical cloud for cloud environment using an apps technique. The contribution of this work has two-folded. Design a multi-objective optimization function with a weighted sum approach using two quality of service parameters, namely as a resource utilization and total cost. So we'll work on only two quality of service parameter, which is the resource utilization and total cost. And then you find an optimal computing device for the optimal fog device that uses quality of service objective to multiple quality of service using an apps technique with higher convergence speed. So we will find the best fog device. First, we'll find the best fog device which have highly resource utilization and lower cost at the end. The goal of this uh, optimization problem to minimize the total cost and latency and maximize the utilization of the computing resource efficiently. Then we will go into details. Firstly, we will talk about the summary of the work that we will do. Firstly, we will develop a multi-tier for cloud model for the offloading the real-time tasks to the suitable computing devices as per the resource requirement. Designed move function, as also known as the fitness function based on the multiple quality of service objectives of the quality of service objective of a real-time IoT application, namely resource utilization and total cost. We further introduce the efficient task offloading strategy on multi-tier fog cloud moving model using APSO technique for improving quality of service parameter in terms of latency, computation time, cost, and resource utilization. Finally, we investigate the parameter and apps technique over multiple real-time data sets and fix their param- parametric values for further analyzing the proposed move strategy. Moreover, we analyze the performance of the proposed method over three state-of-the-art algorithms using various performance. We will not talk about all the summary as we have such short duration, but we will go into details till we get the optimization problem described. Firstly, we're gonna talk about the implementation of. Firstly, we'll talk about multi-tier fog the model. Firstly, we just know that we have here four tiers. The proposed tier in the shown in this figure is composed of four tiers. In IoT device low capacity, we have low capacity fog, which is symbolized as LCF device layer, and we have high capacity fog devices, which is HCF, and we have centralized CDC layer. The IoT layer consists of set of real-time IoT devices, which can generate various type of real-time application for the processing, which is the first tier as shown in this figure for the processing, and the IoT devices have minimum processing and storage capacity. The delay-sensitive IoT applications need to deploy the real-time task on the local fog devices with enough resource capacity that can process the task efficiently with minimum latency. In this work, we classify the fog devices into two levels. On their based on their resource capacity, we have LCF, which is low capacity, and HCF devices, which is high capacity. Here we assume that LCF devices, including mobile devices, tabs, Raspberry, have a limited processing capacity and are deployed nearer to the IoT devices. And LCF devices are deployed on tier 2 of the model and minimize the latency of the task with the minimum processing transmission. So this is a tier 2. The HCF devices, including the desktop, workstation, private cloud of the educational institute or industries, have more processing capacity with higher latency as compared to with the LCF as shown in this figure. It is in the tier 3, and we have enough processing capacity for the processing the tasks and the minimum latency and cost compared with the CDC. In the last tier, which is tier 4, consists of centralized CDC, which has enough resources for processing any type of resource intensive application. And then we'll talk about the execution model. Okay, let us consider. Then we will talk about this is the execution which will describe the optimization parameter after. We have let us consider that we have n IoT devices in the system, and by the set of I, we have I1, I2, I3, which is I is indicate the IoT device. Each IoT device, we know that it generates a real-time task in such a in such a period of time, which is Tn for the further processing. The main focus of the work is to find an optimal computing device for each task based on multiple quality of service parameters. Here we focus in two primary objectives, namely total cost and resource utilization for the computing devices while processing the task, which will be discussed in the next slides. Now we will talk about the resource utilization. Given a set of fog devices which have F1, F2, F till Fn, and each element of Fi belong to the set F, and I ranges from 0 to n. We have like this is indices of the fog devices. Uh, in as we know, we have fog devices in tier 2 and tier 3. Okay, then we will talk about the resource capacity for the fog devices. We have U, it's simple. We have UIC and UIMM. What's the difference between them? We will talk about UIC denotes the maximum CPU capacity, and UIMM represents the maximum memory usage or the maximum memory capacity that we have. Then we will talk about the CDC, which consists of number of cloud servers, which in symboled as H1 and H2 and H3 that can run multiple intensive tasks in parallel. Moreover, in parallel. Moreover, the maximum CPU and maximum capacity, it's UG instead of UI. So we have UG, which is UGC, which is the maximum capacity of CPU, and UGMM, which is the maximum memory usage. Then we will talk about the workload. The maximum workload consuming by the computing devices within a time interval t, which is t1 equal minus t2. We have alpha, like as shown in this figure, and we have the maximum capacity of CPU and the maximum capacity of memory. This L is it can be get the workload of I and J, which is get the workload for the CDC devices servers, and get the workload, the maximum workload for the fog devices. So L here, UL here is indicate I or J. It can work with I or J. And alpha here is the user defined constant whose value is lies between 0 and 1. Okay, and the value of this U is interval from 0 to 100, as this is the capacity as the percentage of the usage. Now, each task requests a specific for a specific set of resources for processing in the computing devices, such as we have R1C and R1MM. This is every task show which the workload is used for this task, using capacity and using the memory in terms of sets, and for every task shows how the usage of the capacity and how the usage of memory, as R1C, R1MM for the first task, R2C, R2MM for the second task, and so on, based on the processing. Assume that a certain stamp, we talk about the time TK number of the tasks are received by IoT gateways for the offloading computing devices. We have T1, T2, T3. Each task should be offloading suitable computing device based on the resource requirement. And the requested workload of the task K is shown in this figure. We have RK, C, and RKMM. This is the requested that we need to get for the task. Then we'll talk about go into more details about the decision variable, and more nearer to the optimization problem. Here we know that we have xk1, which is the decision variable of the system, which is equal to 1 or 0 if the task is equal to 1 if the task tk is offloaded to a computing device. So if the task is computed already by computing devices, so it will be 1. It between 0 and 1. And as we know, for every computing devices has only one task. So the summation of the all tasks that requested to this device, it will be equal, all of them be 0 except the one that will be requested by this device. Thus, each task needed to be offloaded to the suitable computing device for the further processing. Note that the overall CPU cores consumed by the task TK should be less than or equal to the maximum CPU capacity of the computing device. And this is we said about we have the first constraint. As we see, we don't the maximum, it will not be accepted if it is more than the maximum capacity of the CPU. The same for the memory. The amount of the memory blocks is consumed by the task should be less than or equal to the memory capacity of the computing devices. And this we will say it's the second constraint that we will have in the optimization problem. The overall, the overall workload consumed by the task TK must be less than or equal to the maximum workload of the computing devices, as the requested task that we have should be less than or equal to the maximum workload for these computing devices, as this is a third constraint, and the resource utilization of the computing devices for the processing task is defined as follows: RUKI. This is, as we say, this is the resource utilization for the computing. It's shown here as the mainly the mainly resource utilization equation. So we need to maximize this resource utilization equation. Then we will talk about the cost. The cost of the real time depends on the processing time on the selected computing devices. So the cost here is depends on the time of the consuming time with the multiple resources and latency of for the transmitting the task from the source IoT devices to the selected computing devices. The processing time of the task TK depends on the PKI. So the PKI is SK over CPC over CPI C. What SK? SK as shown here, SK is the size, and CPCI is the CPU capacity of the computing device. Then we will talk about the processing cost of the CPU usage by the task is defined as the following. So this is the processing cost, this equation for the tau 1, where it represents the CPU cost device for the unit interval. This is tau is unit time interval, which is called tau 1. Then the memory of the computing device is L is consumed by the task Tk until the completion of its processing, as shown in this equation. As this is the memory cost Tk for the primary data storage defined as the follow represents the memory cost of the computing devices one device L, sorry, for a unit time interval tau 2. The total processing cost of the task Tk is represented as the total cost for both the memory and the CPU. The latency between IoT devices K and the selected computing device L depends on the bandwidth of the network and the distance The latency between the device K and LDK L is represented as shown in this equation. So this is the latency of the device, the IoT devices K and the selected computing device L. And here, SDK and PK1 represent as the serialization delay and propagation delay, respectively. The propagation delay is a ratio between the distance among the device K and the DTK1 and DTKL. The bandwidth of the network PK1 as shown in this equation, and we have DTKL, which is as shown in this equation. So the serialization delay is the ratio between the size of the task TK to the transmission rate of the network TTKL in the bit per second. So this is the serialization delay, and this is the propagation delay. At the end, we assume that LCF devices in tier 2 are nearer to the IoT device, so the latency between IoT devices and LCF is zero, and they represent the communication cost per unit time to reach the task to the selected computing devices L for a unit time interval tau 3. The cost of this latency is defined as shown in this equation. So the total cost required for the processing transmitting task is defined as follow TCO. So we need now to minimize this equation as much as we can. Now we will go into the final slide, which presents the optimization problem. As shown here, we need to maximize the resource utilization and minimize the cost. So subject to we have all the constraints which is subject to the utilization, and there is no constraints for the cost as shown, as it's more depends on the latency and the the choice of the fog devices, which give low latency and lower cost. So it's and a high processing time for sure. So this is shown in this paper as the optimization problem, and we don't go into details for the conclusion and the results, as we don't need to understand, as we just need to understand that this is the introduction for the problem, and end by this optimization problem as shown in this figure. Thank you. So